Okay, here we go. Kinesiology 230, chapter number 3, still in bioenergetics. And we talked a little bit about glycolysis in the previous presentation. This is more about glycolysis regulation. With glycolysis, we're talking about the energy system that's specific to glycolytic reactions to create ATP. We talked about these two here in terms of energy demands and both being anaerobic. And with that said, we went into this where we talked about the Krebs cycle, and what really happens here with the pyruvate is what matters. If there's enough oxygen, Krebs cycle. If the exercise intensity is low enough, where bodies can buffer or actually buffer the lactic acid and buffer the byproducts that are being made from exercise, Krebs cycle. If the exercise intensity is too high, lactate. If the intensity is too high and we don't have oxygen or there's not enough oxygen, the pyruvate becomes lactate. So that's the key component with this chart. We talked about this in terms of the net result of slow glycolysis versus fast. Fast, you end up with a low oxygen environment where you have 2 net ATP. We talked a little bit about the differences between fast and slow, and with the slow glycolysis, you're in the Krebs cycle, you're in the mitochondria, and you're creating way more ATP. All right, so just we put those side by side, right? You have C6H12O6, which is sugar, glycogen, if you will, and you have glycolysis happening here. Glycolysis is stimulated through intense muscular activity by the ADP, phosphate, ammonia, and slight increase in pH. When you have glycolysis being inhibited, shown here with this dashed line breaking our arrow, you have a lower pH level, you have an increased level of ATP, you have creatine phosphate, you have citrate and free fatty acids at rest. So now the book lists this out, and I think it's worth noting just a quick little conversation on this. If you look at this, if you have increased levels of ATP, your body doesn't need to go through the process of glycolysis to make ATP. That's what you're saying. And the other part of this is when you have like a heavy duty muscular activity, your body will need ATP. If you're at rest, you don't need ATP. If you're and we talked a little bit about the oxyhemoglobin dissociation curve, and there's another curve that we'll see here in a second in terms of the acidity level of the blood. But if your pH level drops, it means the acidity of your blood is going up, and when you have a higher acidity level of the blood, that inhibits glycolysis, et cetera, et cetera. So, there's a little part in the chapter in the book that kind of elaborates on this. I would say take a moment just to kind of wrap yourself around it. Now, you have glycolysis and phosphofructokinase, and PFK is an enzyme that is responsible for unlocking the rate-limiting step in glycolysis, and the rate-limiting step is this. You have a multi-step process, and PFK is the third enzyme, if you will, the third step in that process, and PFK unlocks that third step to allow glycolysis to happen. So again, if we go back to our theoretical on this, if you have activation of the phosphagen energy system, right, that system is fired up. We need to make ATP, and what happens is it's going to stimulate phosphofructokinase. If you're sitting there right now and you're not really doing anything, you don't have a high demand for ATP, but if you do anything like raise your arm, move around, you have an increased need for ATP. The ATP factory has to be fired up. We need more adenosine triphosphate. The phone call that goes out, the way I just kind of remember this in my head, that goes out happens through the phosphofructokinase. It happens through the enzymes that are available that allow that phone call to happen. And with the phosphofructokinase, that phone call allows the process to go from step number 3 to step number 4 and thereon. So this passage to the right, they highlight this. They know another important consideration in the regulation of any series of reactions is the rate-limiting step. The rate-limiting step in glycolysis is a conversion of fructose 6-phosphate to fructose 1,6-biphosphate, blah, 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 a reaction controlled by the enzyme phosphofructokinase. Thus, activity of PFK is a primary factor in the regulation of glycolysis. And that is a key, very key part of this passage. And it's also a very key question, I believe, on a quiz or a test somewhere down the road. But you just got to understand there's a relationship between phosphofructokinase, ASE, yet again, that is one of those electron transport enzymes that allows, or one of those enzymes that allows electron transport process to happen, that allows glycolysis to happen. It's something that enables a process to happen. So we talked about fast glycolysis and we talked a little bit about like fast and slow glycolysis. So when you look at this, fast glycolysis occurs during periods of reduced oxygen. Got it. That's when we are not really able to go into the Krebs cycle, but we end up with pyruvate. Got it. Fast glycolysis results in a greater number of acidic byproducts as compared to lactate, which is a base. Oh, well, that's kind of weird when you start thinking about like the muscles and having lactic acid and you start to fatigue. But what ends up happening is you have this lower pH that inhibits this glycolytic reaction, which we talked about before. And I'm going to read this passage to the right just to kind of reiterate what we're talking about. Thus, muscular fatigue experienced during exercise, previously thought to be associated with high concentrations of lactic acid in the muscle tissue, is actually a result of decreased tissue pH, meaning it becomes more acidic from metabolic byproducts such as hydrogen ions that are acidic in nature as compared with lactate, which is a base. And what's hard about this is we're so conditioned to think like lactic acid, and that's what we really wrap ourselves around. But it ends up being just from a decrease of pH from the metabolic byproducts. So as pH decreases, meaning we become more acidic, it is believed to inhibit the glycolytic reactions and directly interfere with muscle action, possibly by inhibiting calcium binding to troponin, or by interfering with the actin-myosin cross-bridge formation. You recall that from Module 1, where we have those little cross bridges that are rowing to pull the Zweischen, the lines, right, the in-between the Z's, everything's pulled into the middle, the mitral, the M line. So what happens is the actin-myosin cross-bridge formation can't happen because of the pH level. Also, the decrease in pH levels inhibits the enzyme, the ACE, ASE that we always talk about in the cell's energy systems. So the phosphofructokinase, ASE, those things are the enzymes. So the overall effect is a decrease in the available energy and really the ability for the muscle to create any kind of force during exercise. So you have this kind of series of events that all happens, but this paragraph and a half here does a really good job of encapsulating everything specific to pH levels, and also does a really good job of encapsulating everything specific to what we originally thought of in terms of like that lactic acid was causing the muscles to be inhibited in their contractile ability, but in actuality, lactate's a base. And really we're talking about something else in terms of how the pH changes, and it changes because of the ions found in the hydrogen. So we talked about this in another presentation, but let's kind of look through this, right? And we're talking about acidosis. We're talking 7.0, so that's a shift to the right. This is like the oxyhemoglobin dissociation curve we talked about in Module 1. So here you are, you're working out, and you have these byproducts with the hydrogen ions that are making the blood more acidic. That's what's inhibiting the ability to contract. So it's a little bit of a throwback here, but I think it has its place in our presentation right now. So lactate. Lactate is used for energy in type 1 muscle fibers and cardiac muscle fibers. And it's also used in gluconeogenesis. Well, I'll tell you, you just need to play Scrabble and you guys will kill it. And the book notes that lactate does not contribute to fatigue per se, but clearing it from the blood can give an indication of how quickly a person is recovering. So you can imagine somebody's working out, we do blood draws, when they get done working out, we can do blood draws to see how quickly that lactate is actually clearing the system. And we transport it in the blood to the liver where it's converted into glucose through what's called gluconeogenesis. And again, you can break that out into gluconeogenesis, or what's commonly known as the Cori cycle. So with this, on the right side, lactate, however, is used as an energy substrate, especially in type 1 and cardiac muscle fibers. We know that. It's also used in gluconeogenesis, the formation of glucose from non-sugar substances, which in this case would be the lactate. And it doesn't contribute to muscular fatigue, et cetera, et cetera, et cetera. And everything else, I think I got pretty much tied in over here. So I'm going to jump over to this next one. The lactate itself, in this cyclical process, what we're seeing here is you have fast glycolysis. We create lactate because it can't, the pyruvate can't go into the Krebs cycle because there's not enough oxygen. So the pyruvate becomes lactate. The lactate then goes to the liver, that's processed in the liver, and from the gluconeogenesis that we talked about, the lactate becomes glucose and glycogen, and then it becomes blood glucose, right? So you're kind of switching the lactate to glycogen, glycogen to glucose, it becomes blood glucose, and that goes back into the muscle, and the blood glucose is then converted to glycogen, which allows us to go through the whole process yet again. What did it take me? A minute to explain that? That happens like thousands of times in our body during a muscle contraction. It's just amazing how quickly these things actually happen in the body. So I just want to reiterate, when you go through and you start to look at this stuff, we as instructors fall victim to this, where sometimes we overcomplicate things instead of trying to really overly simplify them for our students, especially in the context of where we are in our course work. We're talking 200 level. I think it's all about keeping it simple. So just think of this in terms of, if it has oxygen, it goes to Krebs. Without oxygen, or the intensity is too high, the pyruvate becomes lactate, and that lactate then has to be processed through the liver. All right, I'm going to go. My dogs let me know it's time for dinner.